first presenter of our research session 1 is Gero, professor in computer science and architecture at the University of North Carolina.
Okay, when I was invited to come, I thought, oh, Korea's, I like Korea. And I thought, my research is not really about cultural DNA until I have a look at what people thought cultural DNA might be. And then I discovered it was. So, my first question was, I read the material, what could this cultural DNA be? Not a straightforward answer to give a question like that. And I didn't like any of the answers I saw, because I felt they didn't capture enough. So I put forward a more generic answer, which is cultural DNA involves any mechanism that transfers culture from one generation to another. And by a mechanism, I mean some form of externalization, which allows people who weren't the creators of it to use it. So it's the standard ways in which knowledge is transferred. And the word generation here, I don't mean in the natural sense, I mean just from one person to one place to another. So if you take that as the starting point, the next question is, where could this stuff be? Where is it? And looking through the first workshop, you got the answer. Well, actually, no, you didn't. What you got was what the first workshop did. And I thought, let's think a little more broadly as to where this stuff might be. And everyone seems to think it's, and I'm talking about design. Although design is a big word and maybe it covers everything. You and I could have a lot of discussion about where design sits in computer science, and I would hope to illuminate you. That's not today. So the cultural DNA is in the design. You see the thing, something is happening. That seems to be a very narrow perception of the world, even though our field is design research. Maybe it's in the observer of the design. Maybe it's really there with the user. And the design is a vehicle. It's not a thing anymore. It's just a vehicle. Or maybe it's in neither of those. It's in the process by which the design is produced. Because if you think of, in an analogical sense, genetics has at least two fundamental characteristics: representation and some kind of process, which of course is getting closer to a Turing machine, except the Turing machine representation and process are the same. There is no difference. Or, in our world, we're accustomed to thinking of the designer as being God, you know. The designer creates things, and our society recognizes this because, you know, this shirt has this little thing on it. It's a polo shirt. So we know something about the fact that we value the designer. You know, in architecture, if I say this is Zaha Hadid building, I don't have to look at the building. I know that it's something special. And we have the same in computer science. Well, it used to be. People said, oh, this was produced by Google. It used to mean something really good. Now it just means they do everything. Maybe it's none of those. Maybe it's in the interaction between the user and the design in this sort of affordances idea. Affordances in computer science is a really new idea. they'll catch up. Maybe in a more profound sense, it's actually the effect it has on individuals and society. What I want to do is to just quickly run through some research that looks at these. The one we're most familiar with is that we're studying this in the design. And I think actually many of the papers which I've just glanced through fall into this category. And each one of these I'm going to show a slide and wave my hands. But they're all based on stuff that people pull out. So this is the standard sort of stuff people do in architecture. These are plans of Frank Lloyd Wright buildings. They're labeled with colors that have some meaning associated with them. This has to use a different approach. It uses a genetic engineering extraction approach to pull out genes which are represented by these, and then you can execute those in an evolutionary system and produce Frank Lloyd Wright buildings, which were Frank Lloyd Wright. And this is an example of transferring, here's the mechanism, transferring something from a design to somewhere else. If, however, we're interested in what the observer sees, the observer is a human being. A human being is nothing like anything else and is full of really intriguing and unusual things that we never thought about, and is involved in perception. Perception is when you, at least this nice simple example, what is out there is not what you see in your head. There's a whole range of processes. So this actually is random white noise, and these are two observers. The observer, these are two observers, these are computational models of observers who've got different experiences and different expectations. And what they pull out of this, because humans by their nature aim to structure everything that they perceive, whether we like it or not, Plato has it nicely, he says it's in the nature of man to know. Know meaning that the world is not random. So what my experience is in looking and getting feedback, and what I'm looking for affects what I see in the world. And here's an example where we show this random noise. They pull out features, so this is a deep learning neural network that runs across this. It's got all this experience. It extracts those features and thinks that they might be connected to some floor plans, Palladio, Frank Lloyd Wright, whoever, based on their experience. Right? And we can pull out this interaction. But maybe it's in the design process. Right? So here's some work. This is Chinese architecture. Right? Simplified. And what we do is we use something like evolutionary programming, although it doesn't do that, it does something else. It actually does genetic engineering over evolutionary programming to pull out what are the transformations from one state. So this is a state machine, and it pulls out the transformations from one state to another, which here have visual meaning, and slowly builds up a set of processes which will produce, when executed, these designs. And now you can use them all over the place. So this is an abstraction above just the hello. No excuses for being late.
I was their professor. I'm the one who gets to scold.
Oh, okay. So, again, what we've done, remember, the goal is to find some mechanism to allow to transfer from one generation to another. And here we do it through processes. Of course, what about the designer? What can we study in the designer and what can we pull out of the designer? So now we're not writing computer programs, we're not building computational models, it's not directly. What we do is we're studying people designing. Area called protocol analysis here. And, out of that, what we are looking for are structures. That's what our knowledge is. Where we take this stuff that comes out, find structures which have some invariance associated with them, which becomes our knowledge, which we can transfer. And what this is, let's not worry about mechanics of what this represents, but what we found is a design pattern exhibited by not just these two designers, but a cohort of 20 designers who all exhibit this pattern of behavior. The pattern of behavior is derived by looking at their activities and building a hidden Markov model of what is behind it. So now we've been able to sort of capture something about the designer. Of course, increasingly, we're interested in this interaction between the designs and the users. And the designs don't have to be these physical things. Increasingly, there's stuff that sits somehow in this world behind this very flat screen, which gives us these affordances. And this is a nice picture which you couldn't possibly understand in the time available, but let me tell you what's in it. This is a computational model. I don't know if you've come across the current theory and sort of cognitive psychology is that there's two kinds of thinking for humans. System 1 and System 2. Not very sophisticated labels, but that's by Daniel Kahneman and Amos Tversky. System 1 thinking is almost no reasoning. It's pattern matching, which is what affordances look like in design, say. In System 2 thinking is what we think of as reasoning. I mean, they're both reasoning, pattern matching is one, and the other involves other kinds of abstraction. And this is a series of interlinked neural networks trying to model what is called constructive thinking that allows you to trace how this system, as soon as it interacts, it thinks the world is the first thing it saw. That's all it has. It starts off tabula rasa. And color recognition is not fantastic, but that's it there. And the next time it interacts, all it has is what it did before. And if that works, then it says good, and it gives more grounding to that. That's what the world is. And as it interacts, so it starts to ground. Ground means give more credence, give more weight to this view of the world. And only after a while does that not work. You know, it hits something, it doesn't work. And that's what this thing says. Oh, now I've got to make up something new. But along the way, this idea of how the world is for this interaction gets more and more weight to it. Until after a while, it doesn't need to do any more reasoning. It becomes a pattern. And it shifts from short-term memory through intermediate memory to long-term memory, and lots of nice things happen. It makes the system extremely efficient because it doesn't need to do much computation to find things. And so this is a model of interaction between users and their worlds, and how affordances, which is when you see something, you know what to do with it, how this develops. It uses a different kind of neural network than we're accustomed to, but it makes no difference. And then finally, this notion of maybe the goal of all this, why it's all there interesting to us, is to change us, to give us experiences. Humans are really powerful adapters, not adopters, adapters. They change. It seems the success of this human endeavor is based on our capacity to change. Can we model this? Because again, if you take the idea of what cultural DNA is, okay, 15 minutes you said, left. Oh! Can you model how our values change as we interact with things? Can we capture that? And that's what this does. Now, here I turn lights off. Is this the switch that blows the building up, or? Okay, that's good. All right. Let me tell you what you're going to see, and I'll describe it. This is a video of a landscape presented graphically of a number of things. The first is the red dots are, it's an abstraction, but the red dots are products. They could be ideas, they could be blending machines. The white dots are consumers, or the bright dots are consumers. The goal of consumers is they have some things they're looking for in order to buy them. That's what a consumer does. And they're wandering around this landscape guided by experience. And as they interact means look on a website, say, and they move across websites, so what they see on that website changes them. And there's two ways you can change there. One is, and you hopefully all had this experience, you look on the website and you say, that's close to what I'm looking for, but not exactly. But that reinforces what you're looking for. Or maybe you see things there that you weren't looking for, but now you are looking for. You change what you're looking for. Those are reflected in changes in the values you use to drive your search. And today, of course, much of our interaction is not with descriptions of the artifact, but with other people through social media. And that's what those lines represent. And they represent different kinds of interaction, depending on the trustworthiness of the interaction that's going on. So that's the first thing. Now let's see if this runs. So that's the sort of thing that goes on. This is a multi-agent based modeling system. Each agent is a multi-layer neural network, and it's got two sets of those to build a rich cognitive model of its behavior. And through that, again, this is not to be read, this is just to show you, although I could have made the slide up, but this is actually a screenshot of what's happening inside an agent. And the thing of interest, again, don't try and read it, I can't read it. This is a multi-dimensional vector of the agent's value systems and how its value systems change depending on the influences that it's been exposed to. So the point about all this is that it turns out all of these ideas about where the cultural DNA might be, we can explore cognitively, computationally. So that the notion of cultural DNA turns out to be open to exploration in the same way as any other abstract idea is open to exploration. So what I want to do then is to finish off with something which is a little different to this. One of the interesting things about the distinction between computation and design, which as designers we don't think much of, and as computer scientists we don't think much about, right? Computer scientists really have no, they think designing is this stuff, right? Where your hands move a lot. Is this. In designing, we work on things in order to produce a specialized result. Right? So when you are designing something, you end up with one thing. Maybe it's reproduced, manufacture maybe, and then it's over. And in computational work, the goal is to generalize. To take something, build an algorithm which can be used everywhere. And the example I give is the map pathfinding algorithm on your phone or anywhere. It's the same algorithm. And I said in Korea, same one as I was in India yesterday, same one as in India, same one as in China. The one algorithm, an amazing idea that you can take something and make it so general that everyone, doesn't matter what they're doing in relation to this, uses it. So now we have this interesting intersection between design specialization, computation as generalization. Let's call design thinking as specialization, computational thinking as generalization. And now when we bring them together, we end up with something like this. But there's something that's happened, which is something we need to think about. When you generalize, you think you've finished. You might improve on it. But when you design, you know you're never finished. Because the introduction of a design, which, by the way, I would call an algorithm of design, the introduction of a design changes the environment into which it's put. And the more you generalize, the less you accept change. Right? The more you generalize, because you've invested so much in it. Now we have a conflict, and that's what I want to finish on. Is yes, we can do this, and we should. It's lots of fun. There's lots of benefits, which I haven't talked about. But at the same time, we should be aware that as we do this, it's really hard to think, oh, we should do something else. That we should say, look, maybe having done this, we've changed the world, and now there's something else that we should be doing. And that's a more general critique than specifically to here. Right? Because when we write algorithms, we sort of think we're finished, and what we need to do is just optimize always. And when we design, we always think we're not finished. There's more to do. So let me finish here with the following. I think the idea of cultural DNA, and as you say, Richard Dawkins had this nice idea of a meme, and there's very interesting work done on memes, by the way, generally. It turns out it's quite easy. I use the word easy in the sense that it's possible to look at quite abstract questions associated with this idea of shift, of how do you transfer stuff that is this amorphous set of ideas into knowledge. Today, the way knowledge is encapsulated is computation. That's not, I mean, there's many PhDs, there are hundreds, but it raises some quite profound questions. Let me stop there.
I think we have one question. We can always ask questions during the break time.
I have a lot of questions I can't really suggest them here, but to what extent computer scientists have been involved in this effort for your DNA research?
Well, the boundary between computer science and computation is very porous. It used to be, when we were young, that you knew who the computing people were. And now, who does computing as opposed to computer science is not clear. Right? So I don't think it's that clean. So we're not doing, what I've shown here is not computer science research. Right? We're not advancing computer science. We're taking ideas and applying them in this field in ways that perhaps haven't been applied before. Right? So, we're using constructed neural networks that change their structure. Well, Rumelhart and McLennan in the 80s, they did this sort of stuff. Turns out no one thought it was useful then, or now it is useful.
I guess a more practical question is, what percentage of computer scientists involved in computer science department in universities actually involved in this?
As a general, I can't answer that generally.
You're feeling.
But the answer is an increasing number. Right? Now, what we're finding is that design provides a different kind of vehicle for teaching of computing. Because in the past it was taught as this is what the world looks like, you have to learn it. And it turns out a lot of ideas in computer science match design. I mean, you mentioned requirements, as if that's separate from design. But requirements engineering, say, is part of design. And there's a theory of that, John Carroll's work and people like that, that you can describe it in exactly the terms you describe design. And whereas computer science, pedagogy has no idea what to do with it. It's just taught, here's the book, learn it. And charismatic people teach it better than non-charismatic people. It turns out there's a theory for how to do that from somewhere else.
We talked about increasing number. You have one more person there.